You are standing on the summit of Maxwell Montes, the highest mountain range on Venus, 11 kilometers above the mean surface of the planet. The ground beneath your feet is dark volcanic rock, rough and angular, and it extends in all directions toward a horizon that fades into orange haze only a few kilometers away. The atmosphere around you is thick, far denser than water on Earth, and the light that filters through 90 kilometers of sulfuric acid clouds above creates a perpetual amber twilight. The temperature here is 380 degrees Celsius, cooler than the lowlands far below, but still hot enough to melt lead under normal Earth conditions. The rocks near you catch the faint light, and some of them carry a subtle metallic sheen, a coating that should not exist at these temperatures anywhere on Earth. This sheen comes from compounds that have condensed from the atmosphere itself, minerals that exist as vapor in the scorching lowlands, that settle here as a kind of frost. You are at the highest point on the entire planet, higher than any mountain on Earth, and the ground drops away in every direction. 11,000 vertical meters down to the vast volcanic plains that cover most of Venus. You are at the highest point of this vast mountain range, in a highland region called Ishtar Terra, and the landscape around you will reveal more about how this strange part of Venus was formed. You are listening to the Drowsy Astronaut, and this is a slow journey across the peaks where heavy metals rain from the sky. Over the next few hours, you will explore Maxwell Montes from the summit downward, understanding the geology, the atmosphere, and the remarkable chemistry that creates metallic frost on these peaks. I hope you're settling in somewhere comfortable tonight, and feel free to share where you are listening from in the comments. If this journey helps you relax or learn something new, a like or subscription encourages us to keep making more of them. For now, we are standing at the highest point on Venus, and the ground beneath your feet is where this journey begins. The view from this height is limited by the thickness of the atmosphere. You cannot see the plains below directly. The air is too opaque, filled with carbon dioxide and trace amounts of sulfur compounds. The horizon curves gently away, and the orange-amber light creates a gradient from slightly brighter overhead to darker toward the horizon. There are no shadows in the traditional sense. The light is too diffuse, scattered by the dense air until it comes from all directions at once. The landscape around you is visible but muted, details softened by the haze. The ground surface is uneven, covered with fractured rock and occasional patches of fine dust. The fractures are thermal, created by the expansion and contraction of the rock as the temperature swings between day and night. Venus rotates slowly, taking 243 Earth days to complete one rotation, and the day-night cycle here is measured in months rather than hours. The temperature varies by about 100 degrees Celsius between the hottest part of the day and the coolest part of the night. And this cycling has fractured the surface rock into angular pieces over millions of years. You kneel and examine the surface more closely. The rock is dark grey or black beneath the metallic coating, likely basaltic in composition, similar to volcanic rock on Earth, but altered by centuries of chemical interaction with the atmosphere. The texture is rough, Sharp edges preserved because there is no water to smooth them, no wind strong enough at this altitude to polish the surfaces. The rock has been here for hundreds of millions of years, unchanged except for the slow accumulation of the metallic layer and the gradual fracturing from thermal stress. The metallic sheen is most visible on the upper surfaces of rocks, where the coating has had the longest time to accumulate. The coating is thin, probably only micrometers to millimeters thick, but it is enough to change how the rocks reflect radar signals from orbit. This reflectivity is what allowed scientists on Earth to identify the phenomenon, observing that Maxwell Montes appeared unusually bright in radar images compared to the surrounding lowlands. The brightness suggested something metallic, and later analysis determined that the peaks were cool enough for certain metal compounds to condense from the atmosphere. The compounds are primarily sulfides, chemical combinations of metals and sulfur. Lead sulfide, also called galena, is the most likely candidate for the bulk of the coating, along with iron disulfide, known as pyrite or fool's gold. These compounds exist as vapors in the hot lowlands, mixed into the carbon dioxide atmosphere in trace amounts, and they rise with convection currents until they reach the cooler temperatures at high altitude. Here at the summit, the temperature has dropped just enough for these vapors to condense, shifting from gas to solid and settling onto the rocks like dew forming on grass. You stand and look around the summit area, trying to gauge the size of the peak. The highest point is not a sharp pinnacle, but a broad area, relatively flat compared to the steep slopes that descend from it. The summit region extends for several kilometers, a high plateau that represents the top of the mountain range. Maxwell Montes is not a single peak, but a range, stretching for hundreds of kilometers across the highland region of Ishtar Terra. And the point you are standing on is simply the highest part of that range. The silence here is absolute. There is no wind at this altitude. The air is too still, locked in slow global circulation patterns that do not create weather as Earth experiences it. There is no sound of wind whistling through rocks, no rain, no thunder, no movement of any kind except the slow thermal creep of the rocks as they expand in the heat. If you were to make a sound, it would travel efficiently through the dense atmosphere, but there is nothing here to create sound except your own presence. The sky above is not visible as a distinct feature. The atmosphere is so thick and so opaque that the transition from surface to space is gradual, and looking up simply shows more of the same orange haze, brightening slightly toward what you know is the direction of the sun. The clouds are far above, 50 to 70 kilometers overhead, a permanent layer of sulfuric acid droplets that completely enshrouds the planet. No direct sunlight ever reaches the surface. All the light is scattered and filtered, and the result is this perpetual twilight. The temperature of 380 degrees Celsius is far above the boiling point of water, far above temperatures that any Earth life could survive. Yet, it is significantly cooler than the lowlands below. The surface of Venus at mean elevation reaches about 465 degrees Celsius, hot enough to melt lead, zinc, and several other metals. The 85-degree difference between the summit and the lowlands is the key to the metallic frost phenomenon, creating a narrow altitude range where compounds that are normally gaseous can exist in solid form. You move slowly across the summit area, observing how the terrain changes. Some regions are smoother, covered with a layer of fine dust that has settled over geological timescales. Other regions are rougher, exposed rock with sharp edges and deep fractures. The dust is so fine that it behaves almost like a fluid under the extreme pressure, filling in cracks and creating smooth surfaces in sheltered areas. The pressure here is about 45 times Earth's sea level pressure, equivalent to being 450 meters underwater in Earth's oceans. The rocks themselves are ancient. The surface of Venus was likely resurfaced by massive volcanic activity between 300 and 600 million years ago, and the features you see now date from that period or shortly after. There are very few impact craters on Venus compared to the Moon or Mars, suggesting that the surface is relatively young in geological terms. The resurfacing event, whatever caused it, erased most of the older features and created the landscape that exists today. Maxwell Montes formed either during that period or sometime after, through processes that compressed and uplifted the crust. The metallic coating you observe is not uniform. Some rocks are heavily coated, their surfaces shining dully in the amber light, while others show only faint traces of the metallic layer. The variation may be due to differences in how long the rocks have been exposed, or it may reflect differences in the local conditions. Slight variations in temperature or atmospheric composition that affect the condensation rate. The coating accumulates slowly, perhaps only a few micrometers per million years, but over the hundreds of millions of years, the summit has existed, the layer has built up. You return to the highest point and look outward again, trying to comprehend the scale. You are standing higher than Mount Everest, higher than any point on Earth's surface, yet the pressure around you is crushing. The temperature is above the melting point of many metals, and the air is unbreathable carbon dioxide with no oxygen at all. This is the most extreme mountaintop environment in the inner solar system, a place where the rules of Earth do not apply, and where the chemistry of the atmosphere creates conditions found nowhere else. The journey continues from here, moving from the immediate observation of the summit to deeper understanding of what lies beneath your feet, and the exploration will reveal the nature of the surface, the origin of the metallic compounds, and the history of these mountains. The summit is the starting point, the highest vantage, and everything else extends downward and outward from this position. The rocks beneath you hold stories written in their composition and structure, and the next step is to examine those rocks more closely. The rock beneath your feet is the foundation of this entire mountain, and understanding what it is made of reveals how Maxwell Montes came to exist. You kneel again and pick up a loose fragment of stone, turning it over in your hands. The fragment is dense and heavy, its mass concentrated in a small volume, and the surface is rough with tiny fractures radiating from points of stress. This is volcanic rock, formed from molten material that cooled on or near the surface of Venus, and its composition is likely similar to basalt, the dark volcanic rock that covers much of Earth's ocean floors. The color is dark gray to black, where the metallic coating is absent, and the texture is fine-grained, indicating that the rock cooled relatively quickly. If it had cooled slowly deep underground, the crystals would be larger, visible to the eye, but this rock shows a uniform fine texture, typical of surface volcanic flows. The rock formed when magma rose from Venus's interior, reached the surface, and solidified in the heat and pressure of the atmosphere. The exact age is uncertain, but the surface of Venus shows relatively few impact craters, suggesting that most of the visible terrain is between 300 and 600 million years old. You set the fragment down and examine the bedrock, the solid rock that forms the bulk of the mountain. The bedrock is fractured extensively, crisscrossed with cracks that range from hairline fissures to gaps several centimeters wide. The fracturing is thermal, caused by the daily temperature cycle as the rock expands when heated and contracts when cooled. The temperature swing of about 100 degrees Celsius is enough to generate significant stress in the rock, and over millions of years, this stress fractures even the hardest stone. The cracks are clean, sharp-edged, with no signs of the weathering that would occur on Earth from water or ice. The surface shows no signs of erosion in the traditional sense. On Earth, mountains are shaped by water flowing down slopes, by ice freezing and thawing in cracks, by wind carrying abrasive particles, and by chemical weathering from rain. None of these processes operate on Venus. There is no liquid water, the temperature is far too high for ice, and the wind at this altitude is negligible. The only erosion is chemical, the slow interaction between the rock and the trace gases in the atmosphere. And this process is so gradual that the surface features remain essentially unchanged over millions of years. You observe the dust that covers some areas, a fine powder that has settled into cracks and low spots. The dust is composed of rock particles broken down by thermal fracturing, and possibly by the chemical interaction with the atmosphere. The particles are incredibly fine, much finer than sand, and they do not blow away because there is so little wind at the surface. Instead, they settle under gravity and accumulate in sheltered areas, creating smooth surfaces that contrast with the rough, exposed bedrock. The dust layer is thin in most places, just a few millimeters to centimeters, but it represents millions of years of slow accumulation. The composition of the rock can be inferred from the way it interacts with radar signals. The Magellan spacecraft, which mapped Venus in the early 1990s, used radar to penetrate the clouds and measure the surface properties. The radar reflectivity depends on the roughness of the surface and the electrical properties of the rock, which are related to composition. Maxwell Montes shows a distinct radar signature different from the surrounding plains, suggesting that the rock here may have a slightly different composition, or that the surface properties are altered by the metallic coating. The rock is likely silicate-based, meaning it is composed primarily of silicon and oxygen, combined with metals like iron, magnesium, calcium, and aluminum. This is the same broad category as most volcanic rocks on Earth, though the exact proportions of elements may differ. Venus's interior is probably similar to Earth's in general structure, with a metal core, a silicate mantle, and a relatively thin crust. And the volcanic rocks on the surface are the products of partial melting in the mantle, just as on Earth. The similarity in composition suggests similar planetary formation and evolution, though Venus's lack of plate tectonics means the surface processes are different. You run your hand across the surface of a large boulder, feeling the roughness and the heat. The rock is hot. 380 degrees Celsius is well above the temperature of boiling water, and touching it without protection would cause immediate, severe burns. The heat is stored in the rock from the constant heating by the thick atmosphere, and the rock radiates that heat back, slowly, maintaining the high temperature even through the long night. The thermal inertia of the rock is high, meaning it takes a long time to heat up or cool down, and this helps stabilize the temperature at the surface. The metallic coating on the rock is most visible on the upper surfaces, where it has been exposed to the atmosphere for the longest time. You examine the coating closely, and it appears as a thin layer with a faint metallic luster, not bright, like polished metal, but dull and slightly tarnished. The coating is composed of compounds that formed from the atmosphere, and the exact appearance depends on which compounds are present. Lead sulfide is dark grey and metallic. Pyrite is brassy yellow, and other sulfides range from brown to silver, depending on their composition. The coating does not cover the rock uniformly. Some areas are heavily coated, others show only traces, and fresh fractures expose the bare rock beneath. This variation suggests that the coating is fragile, easily disrupted by thermal fracturing or by the occasional impact of a small meteorite. Once disrupted, the coating begins to reform as the atmospheric vapors condense again, but the process is slow, and recently exposed surfaces may not yet have accumulated a significant layer. The coating is constantly being formed, disrupted, and reformed, a dynamic equilibrium that has persisted for as long as the summit has been at this altitude. The stability of the surface is remarkable. The rock you are examining may have looked essentially the same for hundreds of millions of years, unchanged except for the slow accumulation of fractures and the gradual buildup of the metallic layer. There is no soil formation, no biological activity, no seasonal freeze-thaw cycles, none of the processes that rapidly alter surfaces on Earth. The rock is stable, locked in place by its own mass and by the lack of processes that could move it. The surface of Maxwell Montes is geologically dead, inactive, frozen in time. You step away from the boulder and look at the broader surface, trying to understand the landscape. The summit area is not perfectly flat. It has undulations and variations in elevation, gentle slopes and shallow depressions. These features are probably structural, related to the way the rock was deformed when the mountain formed, rather than erosional features carved by surface processes. The lack of erosion means that the original features are preserved, and the landscape you see is close to what existed when the rock first solidified or was uplifted to this altitude. The ground beneath you is solid, compressed by the immense atmospheric pressure. The pressure is equivalent to being deep underwater on Earth, and it compresses the rock slightly, affecting its density and strength. The rock does not crumble or break easily under this pressure. It is already in equilibrium with the load, and the strength of the rock is sufficient to support the weight of the atmosphere above. The pressure is uniform, coming from all directions, so there is no net force trying to crush the rock, just a constant compression that affects all materials equally. The surface you observe is ancient and stable, composed of volcanic rock that has been fractured by thermal cycling and coated with metallic compounds condensed from the atmosphere. The rock is similar in composition to volcanic rocks on Earth, but the conditions here have preserved it in a state that would be impossible on Earth, where erosion would have worn it down long ago. The next aspect to explore is the metallic coating itself, the phenomenon that makes Maxwell Montes unique and gives these peaks their distinctive radar signature. The coating is thin, but it is the key to understanding why the summit is different from the lowlands. The rocks around you carry this coating, and it is time to understand what it is, how it forms, and why it exists only at these high altitudes. The metallic frost is the reason you are here, the remarkable chemistry that turns vapor into solid and creates conditions found nowhere else in the solar system. The journey moves from the rock itself to the coating upon it, from the solid foundation to the condensed atmosphere. The metallic sheen on the rocks around you is not paint or tarnish in the traditional sense. It is a layer of solid compounds that condensed directly from the atmosphere. You examine the coating on a nearby rock, and it appears as a thin film, slightly reflective, darker than bare metal, but distinctly different from the bare rock beneath. This coating is composed of metal sulfides, chemical compounds formed when metals combine with sulfur, and the specific compounds depend on what elements are present in Venus's atmosphere and what temperatures allow them to condense. The leading candidate for the coating is lead sulfide, a compound with the chemical formula lead and sulfur, combined as PbS, also known by the mineral name galena. On Earth, galena is a shiny metallic grey mineral that forms in ore deposits, and it is the primary source of lead. On Venus, lead exists as a vapor at the surface temperatures in the lowlands, mixed into the carbon dioxide atmosphere in tiny trace amounts. The lead vaporizes from rocks at the high temperatures, enters the atmosphere, and circulates with the slow global wind patterns. As the vapor-laden air rises and reaches higher altitudes, it cools. The cooling is gradual, following the temperature gradient that exists in Venus's thick atmosphere. But by the time the air reaches the altitude of Maxwell Montes, the temperature has dropped from 465 degrees Celsius at the lowlands to about 380 degrees here at the summit. This temperature drop is just enough for lead sulfide to shift from vapor to solid, condensing out of the air and settling onto any surface it contacts. The condensation is similar to water vapor, condensing as dew on Earth. But here, the dew is made of metal compounds. The temperature at which lead sulfide condenses depends on the pressure and the concentration of the vapor in the atmosphere. At the pressure found at Maxwell Montes, about 45 times Earth's sea level pressure, lead sulfide is predicted to condense somewhere in the range of 400 to 430 degrees Celsius. The summit temperature of 380 degrees is well below this condensation point, so any lead vapor that reaches this altitude will condense and remain solid. The lowland temperature of 465 degrees is above the condensation point, so lead sulfide cannot exist in solid form there. It remains as vapor. You look at the coating more closely, and the appearance suggests a crystalline structure, though the crystals are too small to see individually without magnification. The condensation process forms tiny crystals of lead sulfide, and these crystals accumulate over time, building up a layer atom by atom. The growth rate is extremely slow, limited by the rate at which lead vapor reaches the summit and by the rate at which it condenses. Over millions of years, the layer builds up to a thickness of micrometers to millimeters, enough to be visible and to significantly affect how the surface reflects radar signals. Pyrite, or iron disulfide, is another compound that likely contributes to the coating. Pyrite is composed of iron and sulfur combined as FeS2, and it is known as fool's gold on Earth because of its brassy yellow metallic appearance. Pyrite is more stable than lead sulfide at high temperatures, and it can exist in solid form at slightly higher temperatures than galena. The presence of both compounds in the coating would create a mixture, and the exact proportions depend on the relative abundances of lead and iron in Venus's atmosphere, and on the slight temperature variations across the summit area. The coating exists because of the unique combination of altitude and temperature at Maxwell Montes. Nowhere else on Venus is the temperature low enough for these compounds to condense. The surrounding plains are too hot, and even other elevated regions do not reach high enough to cross the condensation threshold. Maxwell Montes is the highest point on the planet, and it is the only place where the temperature drops into the narrow range where metallic sulfides can exist in solid form. This makes the coating a unique feature, found only on these peaks. The process of condensation is continuous, but very slow. As the atmosphere circulates, it carries metal vapors from the lowlands up to higher altitudes, and when the air passes over the peaks, the temperature drop causes condensation. The freshly condensed material settles onto the rocks, adding to the existing layer. The process has been ongoing for as long as the summit has been at this altitude, potentially hundreds of millions of years, and the accumulation is steady, limited only by the supply of vapor and the stability of the condensed layer. The coating is not permanent in the sense that it can be disrupted. Thermal fracturing can crack the rock and expose fresh surfaces, and the coating on those surfaces is lost. Micrometeorite impacts, though rare, can vaporize small areas of the surface and remove the coating. The slow chemical interaction with the atmosphere may also alter the coating over time, though this process is not well understood. Despite these disruptions, the coating reforms wherever the conditions are right, and the overall coverage persists. The radar reflectivity of Maxwell Montes is what first revealed the presence of the metallic coating. Radar signals sent from Earth or from spacecraft in orbit around Venus bounce off the surface, and the strength of the return signal depends on the surface properties. Metallic surfaces reflect radar very efficiently, creating a strong return signal, while rough rocky surfaces scatter the signal and create a weaker return. Maxwell Montes appears bright in radar images, much brighter than the surrounding lowlands, and this brightness was puzzling until scientists realized that the peaks were cool enough for metallic compounds to condense. You observe the coating on several different rocks, and the coverage varies. Some rocks are heavily coated, their surfaces almost entirely covered with the metallic layer, while others show only patchy coverage, with bare rock visible in many areas. The variation may be due to differences in exposure, with rocks in sheltered positions accumulating less coating than rocks fully exposed to the atmosphere. It may also reflect differences in the rock surface properties, with some surfaces providing better sites for crystal nucleation than others. The compounds in the coating are stable at the summit temperature. Once condensed, lead sulfide and pyrite remain solid as long as the temperature stays below their condensation points. The daily temperature cycle on Venus causes the temperature to vary by about 100 degrees Celsius, but this variation occurs around a mean temperature of 380 degrees, well below the condensation point for these compounds. The coating does not evaporate during the day and recondense at night. It remains solid throughout the long Venusian day. The existence of the metallic frost depends entirely on the altitude of the summit. If Maxwell Montes were lower, just a few kilometers lower, the temperature would be too high for the compounds to condense, and the coating would not exist. If the summit were higher, the temperature would be even cooler, and the coating might be thicker or include additional compounds that condense at lower temperatures. The altitude of 11 kilometers is just right to create the conditions where lead sulfide and pyrite can exist in solid form, and this narrow range makes the phenomenon rare. You stand and look around at the coated rocks, the metallic sheen visible on surfaces throughout the summit area. This coating is the result of chemistry operating at planetary scale. Vapors rising from the lowlands, cooling as they ascend, and condensing onto the highest peaks. The process is simple in concept, driven by the temperature gradient in the atmosphere, but the result is unique in the solar system. No other planet has conditions where heavy metals condense as frost on mountain tops, and Maxwell Montes is the only place where this particular combination of temperature, pressure, and atmospheric composition creates metallic snow. The coating you observe is a direct connection to the atmosphere itself, and understanding the atmosphere's properties and behavior at this altitude is the next step in understanding Maxwell Montes. The air around you is dense and hot, composed primarily of carbon dioxide with trace amounts of other gases, and it is the source of the metallic vapors that create the coating. The journey moves from the solid coating to the gaseous atmosphere, from the surface to the air. The atmosphere around you is the reason the summit is cooler than the lowlands, and understanding this requires understanding how Venus's atmosphere behaves. The temperature of 380 degrees Celsius at the summit compared to 465 degrees in the lowlands might seem counterintuitive because you are closer to the sun at higher altitude, yet the temperature is lower. The explanation lies in how the atmosphere stores and transports heat, and in the fact that the surface, not the sun, is the primary heat source for the lower atmosphere. Venus's atmosphere is incredibly thick, about 90 times more massive than Earth's atmosphere. The surface pressure is 92 times Earth's sea level pressure, equivalent to being nearly 1 kilometer underwater in Earth's oceans. This immense mass of air creates a powerful greenhouse effect, trapping heat radiated from the surface and preventing it from escaping to space. The greenhouse effect raises Venus's surface temperature by about 500 degrees Celsius above what it would be without an atmosphere, making Venus the hottest planet in the solar system, despite being farther from the sun than Mercury. The heat trapped by the atmosphere comes primarily from the surface. Sunlight passes through the clouds and atmosphere and reaches the surface, where it is absorbed by the rocks. The rocks warm up and radiate energy back as infrared radiation, heat that we feel rather than see. The carbon dioxide in the atmosphere absorbs this infrared radiation very efficiently, trapping the heat near the surface rather than allowing it to escape to space. The result is that the ground becomes the main source of heat for the atmosphere, radiating energy upward into the air above. As altitude increases, the temperature decreases. This happens because the air at higher altitudes is farther from the heat source, which is the surface below. The atmosphere is heated from the bottom up, and as you move away from the surface, the heating becomes less direct. Additionally, the atmosphere expands as pressure decreases with altitude, and this expansion causes cooling, a process called adiabatic cooling. The combination of being farther from the heat source and the expansion cooling creates a temperature gradient, where temperature drops with increasing altitude. The rate at which temperature changes with altitude is called the lapse rate. On Venus, the lapse rate in the lower atmosphere is about 7 to 8 degrees Celsius per kilometer of altitude. This means that for every kilometer you ascend, the temperature drops by roughly 8 degrees. From the lowland surface at 0 altitude to the summit at 11 kilometers, the total temperature drop is about 85 degrees Celsius. From 465 degrees down to 380 degrees. The gradient is fairly steady, creating a predictable temperature profile through the lower atmosphere. The pressure also decreases with altitude, though not as steeply as on Earth. At the lowland surface, the pressure is 92 bar, and at the summit of Maxwell Montes, the pressure is about 45 bar. The pressure drops because there is less atmosphere above you at higher altitudes, so the weight pressing down is reduced. Even at the summit, the pressure is still far higher than Earth's sea level pressure of 1 bar, and the atmosphere remains incredibly dense. But the difference between surface and summit is measurable and significant. The thick atmosphere acts as an insulator, holding heat near the surface and preventing rapid temperature changes. The thermal inertia of the atmosphere is very high, meaning it takes a long time to heat up or cool down, and this stabilizes the temperature. The day-night temperature variation on Venus is only about 100 degrees Celsius, far less than on airless bodies like the Moon or Mercury, where temperatures can swing by hundreds of degrees between day and night. The atmosphere evens out the temperatures, absorbing heat during the day and releasing it slowly at night. You feel the density of the air around you, though feeling is metaphorical in this exploration. The air is so dense that it behaves almost like a fluid, and moving through it would require significant force. The density at the summit is about 30 kilograms per cubic meter, roughly 30 times denser than Earth's sea level air. And at the surface, it is even denser, about 65 kilograms per cubic meter. This density is why the pressure is so high. The sheer mass of air pressing down creates the crushing pressures at the surface. The cooling with altitude creates the zone where metallic compounds can condense. The surface temperature is too high for lead sulfide or pyrite to exist in solid form, so these compounds remain as vapors mixed into the atmosphere. As air currents carry the vapors upward, the temperature gradually drops, and at some altitude between the surface and the summit, the temperature crosses the condensation point. Above this altitude, the compounds condense onto any solid surface they encounter, creating the metallic frost. Maxwell Montes extends above this condensation altitude, so the summit and the upper slopes are coated, while the lower slopes and the surrounding plains are not. The altitude where condensation begins is not a sharp line, but a transition zone. The condensation point depends on temperature and pressure, and both vary continuously with altitude. The transition zone is probably a few kilometers thick, with condensation beginning gradually at lower altitudes and increasing as altitude rises and temperature drops further. The summit, being at the highest altitude and coolest temperature, receives the most condensation, while areas just above the condensation altitude receive less. The result is a gradient in coating thickness, with the thickest coatings at the highest elevations. The atmosphere's behavior is shaped by the planet's slow rotation. Venus rotates once every 243 Earth days, and this slow rotation creates unusual atmospheric dynamics. The atmosphere itself rotates much faster than the surface, a phenomenon called superrotation, where high-altitude winds circle the planet in only 4 to 5 Earth days. At the surface, however, winds are very slow, typically only a few meters per second, and the air is nearly still. The slow surface winds mean that the atmosphere at the summit is calm, with little turbulence or mixing. The temperature gradient you observe is a stable feature of Venus's lower atmosphere. It has existed for as long as the current atmospheric conditions have persisted, likely millions or billions of years, and it will continue to exist as long as the thick carbon dioxide atmosphere remains. The stability of the temperature profile is part of what allows the metallic coating to accumulate. The conditions at the summit are consistent enough. The condensation can proceed steadily over geological timescales without being disrupted by major temperature fluctuations. The heating from below also explains why the atmosphere is so well mixed in composition. The heat creates convection, rising currents of warm air that carry material from the surface upward, and sinking currents of cooler air that bring material back down. This convection mixes the atmosphere, ensuring that trace gases, like metal vapors, are distributed throughout the lower atmosphere, rather than being concentrated at the surface. The metal vapors rise with the convection, reach the cooler altitudes, and condense, completing a slow atmospheric cycle. The summit's temperature is not the coldest on Venus. The upper atmosphere is much cooler, with temperatures dropping to minus 100 degrees Celsius or lower at altitudes above 60 kilometers. However, the summit is the coldest point at the solid surface, and this makes it unique. The combination of being a solid surface where materials can accumulate and being cool enough for condensation creates the conditions for the metallic frost. Higher in the atmosphere, the temperature is low enough for other compounds to condense, but there is no solid surface for them to accumulate on. The temperature and pressure at Maxwell Montes are extreme by Earth standards, but moderate by Venus standards. The summit represents a slightly less hostile environment than the lowlands, cooler and lower pressure, though still far too extreme, for any known life or for most materials to survive. The temperature drop of 85 degrees makes a significant difference in chemistry, allowing compounds that are vaporized at the surface to exist in solid form here. This difference is what creates the metallic frost and what makes Maxwell Montes scientifically interesting. The journey now moves from the temperature itself to the atmosphere that creates it, to the composition and properties of the air that surrounds you. The atmosphere is the medium through which heat is transported, the source of the metallic vapors, and the environment that defines conditions at the summit. Understanding what the air is made of and how it behaves at this altitude reveals more about why Maxwell Montes is the way it is. The air around you is composed almost entirely of carbon dioxide, about 96.5% by volume, with most of the remainder being nitrogen, about 3.5%. Trace gases make up less than 1% of the atmosphere, but these traces include sulfur dioxide, carbon monoxide, water vapor, and the metal vapors that create the frost. The composition is fundamentally different from Earth's atmosphere, which is 78% nitrogen and 21% oxygen, and the difference in composition creates vastly different conditions. Carbon dioxide is a heavy gas, with molecules that are heavier than nitrogen or oxygen molecules, and this contributes to the high density of Venus's atmosphere. The gas is compressed by its own weight, creating the high pressures at the surface, and the compression makes the atmosphere even denser. At the summit of Maxwell Montes, the density is about 30 kilograms per cubic meter, comparable to certain liquids on Earth, and the air resists motion with a viscosity that makes it feel almost like water. Moving through this air would be like moving through a thick fluid rather than the thin gas we experience on Earth. The pressure at the summit is about 45 bar, 45 times the pressure at Earth's sea level. This pressure compresses everything, including the air itself, and it affects how materials behave. Gases dissolve into solids more readily at high pressure, and chemical reactions can proceed differently than they would at low pressure. The pressure is uniform, coming from all directions, so you would not feel a crushing sensation in one direction, but the total force on any object is immense. A 1 square meter surface at this altitude experiences a force of about 4.5 million newtons, equivalent to the weight of about 450 cars. The atmosphere is opaque to visible light. Not completely, but enough that visibility is limited to a few kilometers at most. The opacity comes from scattering by the dense air itself and by small particles suspended in the lower atmosphere. The light that does reach the surface is orange-amber, filtered by passage through the thick atmosphere and the sulfuric acid clouds far above. The clouds are located between 50 and 70 kilometers altitude, and they completely enshroud the planet. No visible light photography of the surface is possible from space. Only radar can penetrate the clouds. The sulfuric acid clouds are one of Venus's most distinctive features, though they are far above you now. The clouds form from sulfur dioxide and water vapor reacting in the upper atmosphere, creating droplets of sulfuric acid that float in the air. The cloud layer is perpetual, driven by the chemistry of Venus's atmosphere, and it reflects most of the sunlight that reaches Venus, making the planet very bright when seen from Earth. Only about 20% of the sunlight penetrates the clouds to reach the surface, and this limited solar energy is part of why the surface is darker than you might expect. The air is completely devoid of oxygen. There is no O2 in Venus's atmosphere. The oxygen that exists is bound up in carbon dioxide and other compounds, and there is no free oxygen to breathe or to support combustion. The lack of oxygen is one reason Venus is so different from Earth. Oxygen is highly reactive, and its presence on Earth drives many chemical processes, including respiration, combustion, and oxidation. On Venus, these processes do not occur, and the chemistry is dominated by reactions involving carbon dioxide and sulfur compounds instead. The stillness of the air at the surface is notable. Wind speeds at the summit are only a few meters per second, comparable to a light breeze on Earth, and the air feels motionless most of the time. The slow winds are due to Venus's slow rotation and to the fact that solar heating at the surface is relatively weak. The strongest winds on Venus are at high altitude, in the cloud layer, where super-rotating jet streams reach speeds of 100 meters per second. At the surface, the atmosphere is calm, and weather, as Earth experiences it, does not exist. The temperature of the air is the same as the temperature of the surface, about 380 degrees Celsius at the summit. The air and the ground are in thermal equilibrium, exchanging heat until they reach the same temperature. There is no convection between the ground and the air at the very surface. No updrafts or downdrafts, just a steady state where heat is conducted slowly from the atmosphere to the surface and radiated away as infrared. The thermal stability means that the temperature changes very slowly, even over the course of the long Venusian day. The trace gases in the atmosphere, though present in tiny amounts, are important for the chemistry that creates the metallic frost. Sulfur dioxide is present at about 150 parts per million, and it provides the sulfur that combines with metals to form sulfides. The sulfur dioxide comes from volcanic outgassing, though whether Venus is currently volcanically active is uncertain. Water vapor is present at about 20 to 30 parts per million, far less than on Earth. And the lack of water is another major difference that affects chemistry and geology. The metal vapors, including lead, bismuth, and others, are present in even smaller amounts, but they are detectable and sufficient to create the frost over geological timescales. The atmosphere's density affects how sound would travel. If you could make a sound here, it would propagate very efficiently through the dense air, traveling faster than sound does on Earth, and carrying over longer distances without dissipating. The speed of sound in Venus's lower atmosphere is about 450 meters per second, compared to about 340 meters per second on Earth. The dense medium carries vibrations well, and even quiet sounds would be amplified by the density. However, there is nothing here to create sound. No wind, no flowing water, no life, just the silence of an inactive landscape. The atmospheric composition is globally uniform at the surface. Unlike Earth, where atmospheric composition varies with location due to biological activity, ocean-atmosphere exchange, and other processes, Venus's atmosphere is well mixed and consistent. The slow rotation and the global convection patterns ensure that air from one region mixes with air from other regions over time. And the composition at Maxwell Montes is the same as the composition in the lowlands or at any other surface location. The uniformity simplifies understanding of the chemistry. The same processes operate everywhere, modified only by temperature and pressure. The lack of weather means there is no precipitation of the kind Earth experiences. There are no rainstorms, no snowfalls, no hail, no fog, just the steady state of a dense hot atmosphere sitting on a hot surface. The only thing that falls from the air is the metallic frost, and this falls so slowly and in such small amounts that it would not be visible as falling, only as a gradual accumulation on surfaces over millions of years. The metallic condensation is the only form of precipitation on Venus, and it occurs only at the highest altitudes where the temperature is right. The atmosphere at Maxwell Montes is a harsh environment, hostile to any known life and to most materials. The temperature would destroy any organic compounds. Almost instantly, the lack of oxygen would prevent respiration, and the pressure would crush anything not designed to withstand it. The environment is sterile, chemically active in some ways, but biologically dead, and it has been this way for as long as Venus has had its current thick atmosphere, possibly billions of years. The air around you is ancient and unchanging, circulating slowly through global patterns, but chemically stable. The properties of the atmosphere create the conditions that allow the metallic frost to form, and they define the environment that shapes Maxwell Montes. The air is the medium that carries metal vapors from the lowlands to the peaks, that cools with altitude to create the condensation zone, and that provides the sulfur that combines with metals to form the coating. Understanding the atmosphere is essential to understanding the summit, and the exploration of the air reveals why this place is unique. The journey now moves from the summit downward, following the slopes of the mountain toward the lowlands. You begin descending from the summit, moving down the slopes of Maxwell Montes toward the surrounding plains. The descent will cover 11 vertical kilometers, and the journey will take you through the transition zone, where the metallic coating disappears and into progressively hotter and denser atmospheric conditions. The slope beneath your feet is uneven, rising and falling in undulations, fractured by thermal stress, and covered in places with the same fine dust that exists at the summit. The descent is gradual at first, the terrain only slightly inclined, but steeper sections appear ahead where the mountain drops more sharply. The terrain around you shows the structure of the mountain range. Maxwell Montes is not a single peak, but a series of ridges and valleys extending for hundreds of kilometers across Ishtar Terra. The ridges run roughly parallel to each other, separated by valleys that drop hundreds of meters below the ridge tops. The structure suggests that the mountain formed through compression, where forces pushed the crust together and uplifted it, creating the ridges through folding or faulting. The pattern is visible in radar images from orbit, but here on the surface, it appears as a landscape of long linear features. As you descend the first few hundred meters, the temperature begins to rise. The change is gradual, only a few degrees for each 100 meters of descent. But the trend is clear. The atmosphere is growing warmer, following the lapse rate that governs temperature change with altitude. The pressure is also increasing, the weight of the atmosphere above growing as you move lower, and the air feels denser, though the change is subtle over short distances. The descent will eventually take you through the full range of conditions, from the relatively cool summit to the hellish lowlands. The metallic coating on the rocks begins to change as you descend. At the summit, The coating was widespread, visible on most exposed rock surfaces, but as you move lower, the coverage becomes patchier. Some rocks still show the metallic sheen, but others are bare, the coating absent or so thin it is not visible. The change reflects the temperature gradient. As you descend below the optimal condensation altitude, the temperature rises above the point where lead sulfide condenses efficiently, and the coating stops forming. Fresh condensation is rare here, and only the old accumulated coating remains on some surfaces. You reach a point about 2 kilometers below the summit where the coating has almost completely disappeared. The rocks here are bare, dark grey or black, with no metallic sheen. The temperature is now about 400 degrees Celsius, above the condensation point for lead sulfide, and the metal vapors remain in gaseous form rather than condensing. This altitude marks the lower boundary of the frost zone, the transition from coated to uncoated terrain. Below this point, the rocks are bare all the way down to the lowlands, and the character of the surface changes from the unique summit environment to the more typical Venus surface. The slope steepens and the terrain becomes rougher. The descent here requires navigating around boulders and across fractured areas where thermal stress has broken the bedrock into angular blocks. The fracturing is more intense than at the summit, possibly because the temperature range here is wider, creating greater thermal stress during the day-night cycle. The rocks are stable, locked in place by their mass and by the lack of erosion, but the surface is uneven and progress requires care. You observe the patterns of ridges and valleys more clearly as you descend. The valleys appear to be structural, formed by the way the crust was deformed when the mountain range was created, rather than carved by flowing water or ice. The floors of the valleys are covered with loose rock and dust, material that has accumulated there from the breakdown of the surrounding ridges. The valleys run parallel to the overall trend of the mountain range, suggesting that the deformation forces acted uniformly across the region, compressing and uplifting the crust in a consistent pattern. The temperature continues to rise as you descend further. At 5 kilometers below the summit, the temperature is about 420 degrees Celsius, and the pressure is approaching 60 bar. The conditions are growing more extreme, the heat more intense, and the air denser. The summit's relative coolness is a distant memory, and the environment here is closer to the lowland norm. The rocks radiate heat, glowing faintly in the infrared, and the air shimmers slightly from the temperature gradients. The surface shows evidence of ancient volcanic activity in some areas. Lava flows may have descended these slopes in the past, creating smooth surfaces that contrast with the rougher fractured terrain. The flows are old, hundreds of millions of years or more, and they have been altered by thermal cycling and chemical weathering, but the basic shapes remain. The volcanic origin of the surface rock is clear, and the flows provide evidence that Maxwell Montes was shaped by both volcanic and tectonic processes. You reach an altitude halfway down the mountain, about 5 to 6 kilometers above the lowland plains, and pause to observe the surroundings. The summit is no longer visible, hidden by the haze and the curvature of the slope, and the plains below are not yet in view. You are in the middle zone, neither at the unique summit environment nor at the typical surface, and the conditions here are intermediate. The temperature is about 430 degrees Celsius. the pressure is about 65 bar, and the environment is hostile, but not quite as extreme as either end of the range. The slope ahead continues downward, the terrain transitioning from the highland of Maxwell Montes to the surrounding plains. The descent will cover several more kilometers of vertical elevation, and the temperature will rise another 35 degrees to reach the lowland surface value of 465 degrees Celsius. The transition is gradual, no sharp boundary marks where the mountain ends and the plains begin, just a slow change in elevation and conditions. The mountain blends into the surrounding terrain, part of the broader structure of Ishtar Terra. You observe the base of the mountain as you approach the lower slopes. The elevation here is still several kilometers above the surrounding plains, and the terrain shows a mix of features: ridges that continue down from the highlands, valleys that open out toward the plains, and occasional scarps where the slope drops more steeply. The base region is the transition between the mountain and the plains, and it shows characteristics of both: the rough, fractured terrain of the mountains and the smoother volcanic plains that cover most of Venus. The descent reveals the gradient that exists between the summit and the lowlands, a gradient in temperature, pressure, and surface properties. The summit is unique because of its altitude and the cooler temperature that allows the metallic frost to form, but the rest of the mountain is more typical of Venus: hot, dense, and chemically stable. The slopes carry no coating. They are bare rock, shaped by ancient processes and preserved by the lack of erosion. The journey down the mountain shows how the unique summit environment transitions to the common lowland environment over 11 kilometers of elevation. The exploration of the slopes is complete, and the descent has shown the transition from the summit to the base. The next step is to understand how Maxwell Montes came to exist, the geological forces that created this mountain range, and the history that shaped the landscape. The mountain is ancient, its surface dating back hundreds of millions of years, and the formation story is written in the structure and composition of the rocks. The journey moves from observing the mountain to understanding its origin. Maxwell Montes formed through geological forces that operated hundreds of millions of years ago, forces that compressed and uplifted Venus's crust to create the highest point on the planet. Venus does not have plate tectonics like Earth. The crust is not divided into moving plates, and the mountain did not form through the collision of continental plates, as the Himalayas did on Earth. Instead, Maxwell Montes likely formed through a combination of magmatic processes and crustal compression driven by mantle convection, processes that are similar to some of Earth's mountain-building mechanisms, but operate differently in the absence of plate tectonics. The mountain sits within Ishtar Terra, one of two major highland regions on Venus. Ishtar Terra is about the size of Australia, roughly 8 to 10 million square kilometers, and it rises several kilometers above the surrounding plains. The highlands are composed of thick crust, possibly formed by the accumulation of volcanic material over long periods or by crustal deformation that thickened the crust in this region. Maxwell Montes is located on the eastern edge of Ishtar Terra, and it represents the highest part of the highland, a peak that rises another several kilometers above the surrounding elevated terrain. The formation mechanism most likely involves mantle upwelling, where hot material from Venus's interior rises toward the surface. The mantle is the thick layer of rock between the core and the crust, and it convects slowly, with hot material rising and cooler material sinking. On Earth, mantle convection drives plate tectonics, pushing the plates around the surface. But on Venus, there are no plates, and the convection manifests differently. Rising mantle plumes can push up on the crust from below, creating broad uplifts, and they can also feed volcanism that adds material to the surface. The compression that created the ridges and valleys of Maxwell Montes may have occurred when the crust was pushed together by mantle convection patterns. If mantle material rises in one region and spreads outward, it can push the crust horizontally, creating compressional forces that fold and thrust the crust upward. The parallel ridges visible in radar images suggest that the compression acted in a consistent direction, creating a series of folds or thrust faults that uplifted the crust in long linear features. The process is similar to how mountain ranges form in compressional settings on Earth, but without the context of plate boundaries. The age of Maxwell Montes is difficult to determine precisely, but the surface appears relatively young compared to the ancient, heavily cratered surfaces of the Moon or Mars. Venus's surface as a whole has relatively few impact craters, suggesting that the visible surface is mostly between 300 and 600 million years old. A major resurfacing event likely occurred during that period, possibly a global episode of intense volcanic activity that buried older terrain and created the surface we see today. Maxwell Montes may have formed during this resurfacing event or shortly after, when the crust was still adjusting to the redistribution of material. The volcanic history of Maxwell Montes is evident in the composition of the rocks. The surface is covered with volcanic rock, likely basalt or a similar silicate composition, and this rock formed from magma that reached the surface and cooled. The source of the magma was the mantle, where partial melting created liquid rock that rose through the crust. The volcanic activity may have built up the highlands of Ishtar Terra over millions of years, layer by layer, creating the thick crust that now supports the weight of the mountain range. The lack of plate tectonics on Venus is partly due to the planet's high surface temperature. On Earth, water plays a critical role in plate tectonics. It lowers the melting point of rock and allows the crust to deform and subduct into the mantle. Venus has very little water. The atmosphere contains only trace amounts of water vapor, and the surface is far too hot for liquid water to exist. Without water to lubricate the crust, the rock is stiffer, harder to deform, and less likely to break into separate plates. The entire surface of Venus is essentially one continuous plate, and deformation occurs through local processes rather than global plate motion. The mantle dynamics of Venus are similar to Earth's in some ways, but different in others. Both planets have hot interiors, both have mantle convection, and both experience volcanic activity. However, Venus lacks the organized pattern of mid-ocean ridges and subduction zones that characterize Earth's plate tectonics, and the surface processes are more localized and episodic. The resurfacing event that created most of Venus's current surface may have been a catastrophic episode where the entire planet's crust was recycled over a relatively short geological time, in contrast to Earth's continuous, gradual recycling through plate tectonics. The structure of Maxwell Montes suggests that the mountain is no longer actively forming. There is no evidence of recent volcanic activity on the peaks, no fresh lava flows or active vents, and the surface appears stable and inactive. The mountain may be geologically dead, a relic of past processes that are no longer operating, or it may be in a quiescent period, waiting for future activity. Venus may have episodes of volcanic and tectonic activity, separated by long, quiet periods, and Maxwell Montes may have formed during an active episode that has now ended. The exact mechanism that created Maxwell Montes remains uncertain. Scientists have proposed several models, some emphasizing volcanic construction, others emphasizing crustal compression, and still others combining both processes. The lack of direct surface observations and the limited resolution of radar images make it difficult to determine which model is correct. Future missions with better instruments may be able to resolve the question by mapping the detailed structure of the mountain and analyzing the rock composition more precisely. The comparison to Earth mountains highlights both similarities and differences. Earth's tallest mountain, Mount Everest, is about 8.8 kilometers above sea level, lower than Maxwell Montes at 11 kilometers. However, Everest formed through the collision of the Indian and Eurasian continental plates, a process driven by plate tectonics, and it is actively being uplifted at a rate of a few millimeters per year. Maxwell Montes formed through different mechanisms, and it is not currently being uplifted, at least not measurably. The formation processes are different, reflecting the different geological contexts of the two planets. The crust beneath Maxwell Montes is thicker than the surrounding lowland crust. Radar observations suggest that the highlands of Ishtar Terra have crust that is several tens of kilometers thick, compared to about 20 to 30 kilometers in the lowlands. The thicker crust provides the buoyancy that supports the highlands, similar to how thick continental crust on Earth supports high elevations. The thickness may be due to volcanic construction, where repeated eruptions built up layers of lava, or to crustal deformation that shortened and thickened the crust horizontally while lifting it vertically. The mountain's formation is tied to the broader evolution of Venus as a planet. Venus formed about 4.5 billion years ago from the same cloud of gas and dust that formed the Sun and the other planets. Early in its history, Venus may have been more similar to Earth, possibly with liquid water oceans and a more temperate climate. However, a runaway greenhouse effect eventually heated the planet to its current extreme temperatures, boiling away any oceans and creating the thick carbon dioxide atmosphere that exists today. The timing of this transition is uncertain, but it likely occurred more than 1 billion years ago. The surface you observe is the product of these processes: volcanic activity, crustal deformation, and atmospheric evolution, all operating over hundreds of millions of years. Maxwell Montes stands as a testament to the geological forces that shape planets, forces that operate on timescales far longer than human experience. The mountain was here long before humans existed, and it will likely stand long after humanity is gone, unchanged by the slow passage of geological time. The formation story is ancient, and the mountain's existence is a result of planetary scale processes that built and shaped this world. The understanding of how Maxwell Montes formed comes not from direct observation, but from remote sensing. primarily radar imaging from spacecraft in orbit. The next part of the journey explores how we know what we know about these mountains, the missions that mapped Venus, and the radar techniques that revealed the surface through the thick clouds. The exploration moves from the mountain itself to the methods used to study it from afar. We know about Maxwell Montes because radar can see through clouds. Venus is permanently shrouded in a thick layer of sulfuric acid clouds, and these clouds make it impossible to observe the surface with visible light from space or from Earth. Telescopes that work in the visible spectrum show only the cloud tops, a featureless, white or yellowish sphere with no surface details visible. To map the surface, scientists needed a different method, and radar provided the solution, because radio waves can penetrate clouds without being absorbed or scattered. The first radar maps of Venus came from the Soviet Venera 15 and 16 spacecraft, which orbited Venus in 1983 and 1984. These missions carried radar instruments that sent radio signals toward the surface and measured the reflections. The radar operated at a wavelength of about 8 centimeters, and it could penetrate the clouds and reach the surface, reflecting off the rocks and returning to the spacecraft. The return signal carried information about the surface roughness, the slope, and the electrical properties of the rock, and from this information, images of the surface were constructed. The Venera missions revealed large-scale features including mountain ranges, volcanic plains, and impact craters, and they provided the first clear view of what Venus's surface looked like. Maxwell Montes was identified in the Venera data as a large elevated region with high radar reflectivity, and it was recognized as the highest point on the planet. The Venera maps had relatively low resolution, about 1 to 2 kilometers per pixel, but they were sufficient to show the major features and to generate interest in more detailed mapping. The Magellan mission, launched by NASA in 1989, provided the detailed maps that scientists use today. Magellan arrived at Venus in 1990 and spent 4 years mapping the planet's surface with radar. The radar instrument operated at a wavelength of 12.6 centimeters, and it achieved a resolution of about 100 meters, much better than the Venera missions. Magellan mapped about 98% of Venus's surface, creating a comprehensive dataset that revealed details of the geology, topography, and surface properties. The radar technique used by Magellan is called synthetic aperture radar, which uses the motion of the spacecraft to simulate a larger antenna and improve resolution. The spacecraft sends out pulses of radio waves as it moves along its orbit, and it records the reflections from the surface. The timing of the reflections gives the distance to the surface, allowing altitude to be measured, and the strength of the reflections gives information about surface roughness and composition. By combining many pulses, the data can be processed to create high-resolution images. Maxwell Montes appears bright in Magellan's radar images, much brighter than the surrounding lowlands. The brightness comes from the metallic coating on the peaks, which reflects radar signals more efficiently than bare rock. The high reflectivity was puzzling at first, because most rock is not very reflective at radar wavelengths, and scientists looked for an explanation. The leading hypothesis was that the peaks were cool enough for metallic compounds to condense from the atmosphere, and subsequent analysis supported this idea, showing that the temperature and altitude were consistent with lead sulfide condensation. The radar data also provided altimetry, precise measurements of elevation across the planet. Magellan measured the time it took for radar pulses to travel from the spacecraft to the surface and back, and from this time, the distance could be calculated. By mapping the distance at every point, the shape of the surface was revealed, and topographic maps were created, showing mountains, valleys, plains, and craters. Maxwell Montes showed up as the highest peak, rising 11 kilometers above the mean planetary radius, and the surrounding structure of Ishtar Terra was mapped in detail. The images from Magellan are false color, meaning that the colors do not represent what the surface would look like to the human eye. Instead, the brightness in the images represents radar reflectivity, with brighter areas being more reflective and darker areas less reflective. The images are usually displayed in grayscale or with artificial colors added to highlight features, and they have been used to create maps, scientific papers, and educational materials. The images are the closest thing we have to photographs of Venus's surface, though they are fundamentally different from optical images. The radar data revealed a wide variety of surface features on Venus. Volcanic plains cover about 70% of the planet, smooth areas formed by extensive lava flows. There are thousands of volcanoes, ranging from small cones to massive shield volcanoes, larger than anything on Earth. There are also unique features called coronae, circular structures surrounded by ridges and troughs, possibly formed by rising mantle plumes. The tesserae, regions of highly deformed terrain with complex ridge patterns, are among the oldest surfaces visible on Venus, and they may preserve evidence of earlier geological processes. The Magellan mission ended in 1994, when the spacecraft was deliberately sent into Venus's atmosphere to gather data on atmospheric density before burning up. The data collected by Magellan remains the primary source of information about Venus's surface, and the maps created from that data are still used today. No mission since Magellan has provided higher resolution surface mapping, though other missions have studied Venus's atmosphere, clouds, and magnetosphere. Future missions are planned to return to Venus and improve on Magellan's work. NASA's Veritas mission and ESA's Envision mission are both designed to map Venus with higher resolution radar and to study the surface composition in more detail. These missions may launch in the late 2020s or early 2030s, and they will provide new data that could answer questions about volcanic activity, surface composition, and the history of Venus's geology. The missions may also provide better maps of Maxwell Montes and more precise measurements of the metallic coating. The knowledge we have of Maxwell Montes comes entirely from remote sensing. No spacecraft has ever landed on the peaks, no rover has explored the slopes, and no human has stood on the summit. The environment is too hostile for most spacecraft. The heat and pressure would destroy unprotected electronics within hours, and the sulfuric acid in the atmosphere is corrosive. The Soviet Venera landers managed to survive on the surface for a few minutes to a few hours, long enough to send back images and data, but none landed on Maxwell Montes. They targeted lowland sites where landing was easier. The radar view of Maxwell Montes is a technological achievement allowing us to see through impenetrable clouds and map a surface that is otherwise invisible. The images show a world shaped by volcanic and tectonic forces, a world without water or life, a world where the highest peaks are frosted with metals that fall from the sky. The radar data has transformed our understanding of Venus from a mysterious cloud-covered planet to a world whose surface is known in some detail. And Maxwell Montes is one of the most interesting features that the mapping revealed. The journey now moves from the methods of observation to the broader context of Maxwell Montes within Ishtar Terra. The mountain is part of a larger highland region, and understanding that region helps explain why Maxwell Montes exists where it does. The exploration expands from the peak to the surrounding terrain, from the single mountain to the continental scale structure it belongs to. Maxwell Montes is the highest point in Ishtar Terra, a highland region that rises several kilometers above the surrounding plains. Ishtar Terra covers an area of about 8 to 10 million square kilometers, roughly the size of Australia, and it is one of only 2 major highland regions on Venus, the other being Aphrodite Terra, which lies near the equator. Ishtar Terra is located in the northern hemisphere of Venus, centered at about 70 degrees north latitude, and it dominates the landscape of the northern high latitudes. The highlands are elevated because the crust beneath them is thicker than the crust in the lowlands. The thick crust provides buoyancy, allowing the highlands to float higher on the mantle, similar to how continents on Earth float higher than ocean basins because of their thicker, lighter crust. The thickness of the crust beneath Ishtar Terra is estimated to be several tens of kilometers, perhaps 50 to 60 kilometers in some areas, compared to 20 to 30 kilometers in the lowlands. This thickening may have occurred through volcanic construction, crustal compression, or a combination of both. Maxwell Montes sits on the eastern edge of Ishtar Terra, forming part of the mountain rim that surrounds the central plateau called Lakshmi Planum. Lakshmi Planum is a high flat region, about 4 kilometers above the mean planetary radius, and it is one of the largest volcanic plains on Venus. The plateau is surrounded by mountain ranges, Maxwell Montes to the east, Freya Montes to the north, Acna Montes to the west, and Danu Montes to the south. The arrangement suggests that Lakshmi Planum is a tectonic basin, possibly formed by crustal collapse or by the weight of volcanic material loading the crust and causing it to sag. The terrain within Ishtar Terra is varied. In addition to the mountain ranges and the central plateau, there are regions of tesserae, highly deformed terrain with complex patterns of ridges and valleys that intersect at various angles. Tesserae appear in radar images as bright, rough-textured areas, and they represent some of the oldest and most heavily deformed crust on Venus. The name comes from the Greek word for tiles because the intersecting ridge patterns resemble a mosaic of tiles. Tesserae are found in several places on Venus, but they are particularly extensive in parts of Ishtar Terra. The tesserae are thought to have formed through intense crustal deformation, possibly involving multiple episodes of extension and compression that created the complex ridge patterns. The exact processes are uncertain, but the tesserae preserve a record of ancient geological activity, and studying them may provide clues about what Venus's surface was like before the major resurfacing event that created most of the current plains. The tesserae may be remnants of older crust that survived the resurfacing, or they may have formed during the resurfacing event itself. Lakshmi Planum, the plateau at the center of Ishtar Terra, contains two large volcanic calderas, Colette and Sacagawea. These calderas are circular or irregular depressions formed by the collapse of the surface above a magma chamber after an eruption. Colette is about 150 kilometers across, and Sacagawea is about 200 kilometers across. Both are among the largest calderas on Venus. The calderas are relatively smooth-floored, filled with lava flows that erupted after the initial collapse, and they show that volcanic activity has occurred on Lakshmi Planum relatively recently, in geological terms. The mountain ranges surrounding Lakshmi Planum may have formed in response to the loading of the crust by the volcanic material on the plateau. As lava accumulated on Lakshmi Planum, the weight pressed down on the crust, and the surrounding crust may have been pushed upward in a compensating response. This mechanism is similar to how mountain ranges form around large volcanic loads on Earth, such as the Hawaiian Islands, which create flexural bulges in the surrounding seafloor. The mountains of Ishtar Terra may be partly the result of this flexural response to the volcanic load. The highlands of Ishtar Terra are surrounded by lowland plains, vast smooth areas covered with volcanic lava flows. To the north lies Sedna Planitia, a large lowland basin that extends to the North Polar region. To the south and east, other plains spread out, covering the mid-latitudes of Venus. The transition from highlands to lowlands is relatively abrupt in some areas, with scarps or steep slopes marking the boundary, while in other areas, the transition is gradual, with the elevation declining over hundreds of kilometers. The structure of Ishtar Terra suggests a complex geological history involving volcanic activity, crustal deformation, and possibly mantle upwelling. The region may have been the site of a large mantle plume, a rising column of hot mantle material that pushed up the crust and fed extensive volcanism. The plume may have created the initial uplift, and subsequent volcanic activity built up the plateau and surrounding features. The mountain ranges may have formed through compression related to the plume's activity or through the flexural response to the volcanic load. Maxwell Montes, as the highest point in Ishtar Terra, represents the culmination of the processes that created the highlands. The mountain reaches 11 kilometers above the mean planetary radius, higher than any other point on Venus, and it stands as a monument to the geological forces that shaped this region. The height is partly due to the thick crust beneath Ishtar Terra, and partly due to the local uplift that created the mountain range. The combination of regional uplift and local deformation created the conditions for the peak to rise so high. The surrounding highlands provide context for understanding Maxwell Montes. The mountain is not an isolated feature. It is part of a larger system of highlands, plateaus, and tesserae that together form Ishtar Terra. The region is one of the most complex and geologically interesting areas on Venus, and it has been the subject of extensive study using the Magellan radar data. Understanding Ishtar Terra helps explain why Maxwell Montes exists and why it reaches the altitude it does. The name Ishtar Terra comes from Ishtar, the Babylonian goddess of love and war, following the convention of naming features on Venus after women from mythology and history. Maxwell Montes itself is the only feature on Venus named after a man, James Clerk Maxwell, the physicist who developed the theory of electromagnetism and whose work laid the foundation for understanding radio waves, the technology that allowed us to map Venus's surface through the clouds. The exception was made before the naming convention was standardized, and it has been retained for historical reasons. The highlands of Ishtar Terra will likely remain a focus of future exploration efforts. The region's complex geology, the presence of the highest peaks, and the potential for learning about Venus's history make it a scientifically valuable target. Future missions may include orbiters with improved radar, landers that can survive long enough to analyze surface composition, or even balloons that drift through the upper atmosphere, observing the surface from above. Each new observation will add to our understanding of this region and of Maxwell Montes. The exploration of Ishtar Terra as context for Maxwell Montes is complete, and the journey now turns to a different aspect: the timescales over which these features have existed and the stillness that defines them. The mountains are ancient and unchanging, and the next part explores what that means: the deep geological time that governs Venus's surface and the patience required to see change. The journey becomes more contemplative, reflecting on time and stillness. The surface beneath you has been here for hundreds of millions of years, and in all that time, it has changed very little. The rocks you observe, the fractured terrain, the slopes and ridges, all of these features formed long ago and have remained essentially the same ever since. The timescale is difficult to grasp. Hundreds of millions of years is longer than complex life has existed on Earth. And yet the surface of Maxwell Montes has endured through all that time, accumulating its metallic frost grain by grain, fracturing slowly under thermal stress, and otherwise remaining still. The age of Venus's surface is estimated from the number of impact craters. When a surface is young, it has few craters because there has not been enough time for meteorites to strike it. When a surface is old, it accumulates craters over time, and the density of craters provides a rough estimate of age. Venus has relatively few craters. About 1,000 have been identified across the entire planet, and this suggests that the surface is relatively young compared to the Moon or Mars. The estimated age is between 300 and 600 million years, though some regions may be older or younger. Maxwell Montes may have formed during the major resurfacing event that created most of Venus's current surface, or it may have formed sometime after. The exact age is uncertain because scientists cannot date the rocks directly without samples, but the mountain is at least several hundred million years old, and possibly older. In all that time, the mountain has stood essentially unchanged, the same ridges and valleys, the same fractured rock, the same metallic coating accumulating slowly at the summit. The stability is profound, a stillness that spans geological ages. The lack of erosion on Venus means that surface features are preserved far longer than on Earth. On Earth, mountains are constantly being eroded by water, ice, and wind, and even young mountains show signs of erosion within a few million years. The Himalayas, for example, are being uplifted at a few millimeters per year, and they are also being eroded at a similar rate, and the balance between uplift and erosion determines their current height. On Venus, There is uplift that created the mountains in the past, but there is essentially no erosion, so the mountains remain. The only changes at Maxwell Montes occur on very slow timescales. Thermal fracturing adds cracks to the rock over millions of years, gradually breaking the surface into smaller and smaller pieces. Chemical weathering, the interaction between the rock and the trace gases in the atmosphere, alters the mineral composition very slowly, creating new compounds on the surface. The metallic frost accumulates at an estimated rate of micrometers per million years, a buildup so slow that it would be invisible over human lifetimes, but significant over geological time. You observe the rocks around you, and the stillness is palpable. A boulder sitting on the slope may have been in that exact position for hundreds of millions of years, undisturbed by wind, unshifted by water, unmoved by ice. The boulder has fractured internally from thermal stress, and it has accumulated a coating of dust and metallic frost. But it has not rolled down the slope. It has not been buried by sediment. The rock has simply sat there, patient and still, through the passage of deep time. The absence of weather means there are no storms, no sudden changes, no seasons. On Earth, weather is a constant source of change. Rain falls, snow accumulates, storms blow through, and the surface is constantly being altered. On Venus, the concept of weather as humans know it does not apply. There is only the slow global circulation of the atmosphere and the steady state of temperature and pressure at the surface. The stillness is total. Nothing moves except on geological timescales. The atmosphere at the summit barely moves. The wind speeds are only a few meters per second, and the air is in a stable state. The temperature changes slowly over the course of the long Venusian day, rising during the months-long daytime and falling during the months-long night. But the cycle is so gradual that the changes are imperceptible on human timescales. The atmosphere is thick and sluggish, resisting change, and the conditions at the summit remain nearly constant day after day, year after year, millennium after millennium. The impact craters on Venus are all relatively fresh, with sharp rims and little erosion, because there is no process to wear them down. On Earth, craters are eroded quickly, and old craters are barely recognizable, filled with sediment or worn away by water and ice. On Venus, even ancient craters look fresh. The impact that created a crater 400 million years ago left a mark that is still clearly visible today. The ejecta blanket still surrounds the crater, the central peak still rises from the floor, and the rim is still sharp. The timescales on Venus are so long that human history is insignificant in comparison. All of recorded human history, the rise and fall of civilizations, the development of technology, the entire span of human culture, fits into the last few thousand years. The mountain was here long before the first humans evolved, and it will be here long after humanity is gone, unchanged by our presence or absence. The perspective is humbling, a reminder that geological processes operate on scales far beyond human experience. The patience of geological processes is evident in the slow accumulation of the metallic frost. If the coating accumulates at a rate of 1 micrometer per million years, then a coating 1 millimeter thick takes 1 billion years to form. The actual rate may be faster, perhaps a few micrometers per million years, but even at the faster rate, the timescales are immense. The frost you observe on the rocks may represent hundreds of millions of years of slow condensation, each atom of lead or iron settling onto the surface and adding to the layer. You look around the summit area and everything is ancient. The ground beneath your feet solidified hundreds of millions of years ago. The metallic coating began forming shortly after the summit reached its current altitude, and the thermal fractures developed gradually as the temperature cycled through countless days and nights. Nothing here is new. Nothing has formed recently on any timescale that humans would recognize as recent. The landscape is a museum of deep time, preserved by the absence of the processes that erase history on Earth. The silence here is complete. There is no wind to whistle through rocks, no rain to patter on stone, no rivers to rush or ice to crack, just the stillness of a landscape where nothing moves. If you were to make a sound, it would travel efficiently through the dense atmosphere, but there is nothing here to create sound except your own presence. The silence has persisted for hundreds of millions of years, unbroken except by the occasional impact of a meteorite, events so rare that millions of years may pass between them. The stability of the surface extends to the temperature as well. The summit temperature of 380 degrees Celsius is not a recent condition. It is a long-term equilibrium reached between the heat rising from below and the cooling with altitude. The temperature has likely been close to this value for as long as the summit has existed at its current elevation, and it will remain close to this value for as long as Venus's current atmospheric conditions persist. The thermal stability is part of what allows the metallic frost to accumulate. The condensation occurs continuously because the temperature stays in the right range. The rocks themselves hold stories written in their structure and composition. The volcanic origin is clear from the basaltic composition. The fracture patterns tell of thermal cycling, and the metallic coating reveals the atmospheric chemistry. Each feature is a record of processes that operated over geological time, and together they tell the story of Maxwell Montes, a story of formation, persistence, and slow change. The rocks are archives, preserving information about Venus's history for anyone who can read it. You step carefully across the summit, observing how the terrain has remained unchanged. The surface roughness has not been smoothed by flowing water. The sharp edges have not been rounded by wind-blown sand, and the fractures have not been filled by sediment. The surface is as rough and angular as it was when it formed, preserved in a state that would be impossible on Earth. The preservation is nearly perfect, limited only by the slow thermal fracturing and chemical weathering that operate over millions of years. The stillness you observe is the stillness of a world where geological processes have reached equilibrium. The forces that created the mountains have ceased. The volcanic activity that resurfaced the planet has ended, and the surface is now in a state of slow decay, fracturing and weathering at a pace so gradual that change is nearly imperceptible. Maxwell Montes is geologically dead, or at least dormant, and the stillness is the stillness of inactivity, of forces that once operated but now lie quiet. The exploration of stillness and time reveals that Maxwell Montes is not a dynamic place in any human sense. The surface is ancient, the processes are gradual, and the environment is stable over timescales that dwarf civilization. The journey now moves to a gentle comparison with Earth, offering perspective on two worlds with very different conditions, two mountains shaped by different forces, and two environments that demonstrate the range of what is possible on rocky planets. The comparison is offered softly, without drama, just observation of difference. Maxwell Montes is higher than Mount Everest, the tallest mountain on Earth. Everest stands 8.8 kilometers above sea level, while Maxwell Montes rises 11 kilometers above Venus's mean radius, making it over 2 kilometers taller. The difference is significant, and it makes Maxwell Montes the tallest mountain on any rocky planet in the inner solar system that does not have plate tectonics. The comparison highlights that different processes can create mountains of different scales, and that height is not determined solely by one formation mechanism. The formation of these two mountains followed completely different paths. Mount Everest formed through the collision of the Indian and Eurasian continental plates, a process driven by plate tectonics where moving crustal plates push into each other and uplift the crust between them. The Himalayas, the mountain range that includes Everest, are still rising today at a rate of a few millimeters per year as the collision continues. Maxwell Montes formed through crustal compression or volcanic processes that operated without plate motion. And the mountain is not currently being uplifted, it is simply the frozen result of ancient forces. The environment at the summit of Everest is harsh by Earth standards. The temperature can drop to -60 degrees Celsius. The air pressure is only about 1/3 of sea level pressure. And the oxygen is scarce enough that climbers need supplemental oxygen to survive above certain altitudes. Yet compared to Maxwell Montes, Everest is temperate. The temperature on Venus is 380 degrees Celsius. The pressure is 45 times Earth's sea level pressure, and there is no oxygen at all. The conditions are so different that they define completely separate categories of mountain environments. The snow on Everest is water ice, frozen from the moisture in Earth's atmosphere. The snow accumulates over seasons, building up layers that can be meters thick in sheltered areas, and it is shaped by wind into cornices and drifts. The frost on Maxwell Montes is lead sulfide and pyrite, condensed from the metallic vapors in Venus's atmosphere, and it accumulates over millions of years, building up layers that are micrometers to millimeters thick. The materials are fundamentally different, water versus metal compounds, and the timescales are fundamentally different, seasons versus geological ages. Erosion on Earth is rapid compared to Venus. Water flows down the slopes of Earth's mountains, carving valleys and transporting sediment to the lowlands, creating river systems that reshape the landscape over thousands to millions of years. Ice forms in cracks and expands when it freezes, breaking rock apart through a process called frost wedging, one of the most effective erosion mechanisms on Earth. Wind carries abrasive particles that polish exposed surfaces and wear down rock over time. And biological activity, including plant roots and burrowing animals, also contributes to breaking down rock. On Venus, none of these erosion processes operate. There is no liquid water to flow, no ice to freeze and thaw, minimal wind at the surface, and no biological activity. The erosion is purely chemical, the slow interaction between the rock and the trace gases in the atmosphere. And this process is so gradual that the surface changes imperceptibly over millions of years. The difference in erosion rates means that Maxwell Montes preserves features that would have been erased long ago on Earth, and the ancient surface remains visible. The age of Earth's mountains is generally measured in millions to tens of millions of years. The Himalayas are about 50 million years old, relatively young in geological terms, and they are still actively rising. The Rockies are about 70 million years old, and older mountain ranges like the Appalachians, which have been heavily eroded, are several hundred million years old. Maxwell Montes is at least several hundred million years old, possibly similar in age to the oldest mountain ranges on Earth, but the preservation is far better because erosion has not worn the features down. You observe the rocks around you on Maxwell Montes, and you think about the mountains on Earth. On Everest, the rocks show layering from sedimentary deposition, fossils from ancient marine environments, and evidence of metamorphism from heat and pressure during the collision that formed the Himalayas. On Maxwell Montes, the rocks are volcanic, formed from molten material that cooled on the surface, and they show no layering, no fossils, no evidence of the complex geological history that Earth's rocks carry. The simplicity of Venus's geology reflects the planet's different evolution. Earth has life, and life is a major factor in shaping the surface. Plants stabilize soil with their roots. Forests influence weather patterns through transpiration and shading, and biological activity contributes to erosion through both physical and chemical means. Earth's mountains support ecosystems from base to near summit, with different species adapted to different elevations, different temperatures, and different amounts of precipitation. The presence of life adds complexity to Earth's surface processes and creates landscapes that are shaped by both physical and biological forces. Venus has no life, the surface is sterile, and there is no biological influence on the landscape. The difference is profound in terms of how the surface evolves. Life adds constant change and complexity to Earth, while Venus's surface is governed purely by physical and chemical processes. The absence of life on Venus means that the only changes are geological, slow, and patient, operating on timescales that are long, even by geological standards. The landscape is simpler, shaped by fewer processes, and easier to understand in some ways because of that simplicity. The atmosphere of Earth is breathable, composed of 78% nitrogen and 21% oxygen, with trace amounts of other gases, including carbon dioxide and water vapor. The atmosphere supports a climate with weather, seasons, and a water cycle that distributes moisture around the planet. The atmosphere of Venus is toxic, composed of 96% carbon dioxide with sulfuric acid clouds, and it creates a climate that is hot, stable, and hostile. The difference in atmospheres leads to different surface conditions, different erosion processes, and different timescales for change. The exploration of Earth's mountains is direct and accessible. Climbers ascend on foot. Instruments are placed on the summits to measure weather and seismic activity, and samples are collected for analysis in laboratories. The exploration of Maxwell Montes is remote, conducted by radar from orbit, and no human has set foot on the surface or even landed a robotic spacecraft there. The difference reflects the accessibility of the two environments. Earth is hospitable enough to allow direct exploration, while Venus is so hostile that only remote sensing is practical with current technology. The water cycle on Earth is a dominant force in shaping the surface. Water evaporates from oceans, condenses into clouds, falls as rain or snow, and flows back to the oceans through rivers and groundwater. This cycle transports enormous amounts of material, carving canyons, building deltas, and reshaping coastlines over time. Venus has no water cycle. The tiny amount of water vapor in the atmosphere does not condense or precipitate, and there is no transport of material by flowing water. The absence of this cycle is one of the most significant differences between the two planets. The comparison between Everest and Maxwell Montes highlights the diversity of planetary environments. Both are mountains, both are the tallest peaks on their respective worlds, but the conditions are vastly different. One shaped by water and ice and ongoing tectonic activity, the other shaped by ancient volcanic and tectonic forces and preserved by the absence of erosion. The comparison is not meant to judge one as better or worse, just to show that planets can create similar features through different processes and in different environments. Earth is rare in the solar system, possibly rare in the galaxy, because it has liquid water on its surface, a moderate climate, and life. Most rocky planets and moons are more like Venus, either too hot or too cold for liquid water, dry or icy, and lifeless. Maxwell Montes represents the more common type of environment, while Earth's mountains represent the rare conditions that allow water, erosion, and life to shape the landscape. The rarity of Earth makes it precious, and understanding that rarity requires studying other worlds like Venus. The gentle comparison has shown the differences between two peaks on two worlds. The mountains are both impressive, both the result of geological forces operating over long periods, but they exist in completely different contexts. Earth's mountains are dynamic, constantly changing through uplift and erosion, inhabited by life, shaped by water and ice. Venus's mountains are static, unchanging except on the longest timescales, lifeless, shaped by heat and ancient forces. The difference is instructive, showing the range of what is possible. The journey now moves to the final part, a quiet reflection on what Maxwell Montes represents and what this exploration has revealed. The mountains exist, distant and unreachable for now, but known through the data collected by spacecraft. The exploration has been a slow journey through the environment, the geology, the chemistry, and the context, and now it comes to a peaceful close. The final part is contemplative, offering perspective on the mountains and on what they teach us about planets. You are standing on the summit of Maxwell Montes once more, the journey through these mountains nearing its end. The dark volcanic rock stretches out around you. The orange-amber light, filtering through the thick atmosphere, creates the perpetual twilight, and the metallic sheen on the rocks catches what little illumination exists. This place is real. It exists right now, 11 kilometers above the plains of Venus, frosted with lead sulfide and pyrite, baked by the heat of a greenhouse atmosphere. The mountains are distant, 40 million kilometers from Earth at closest approach, but they are known through the radar signals that revealed them. Maxwell Montes represents a different kind of mountain than what exists on Earth. The mountains formed through processes that do not require plate tectonics. They exist under conditions that would destroy any Earth-based life, and they have been preserved for hundreds of millions of years by the absence of erosion. The peaks demonstrate that nature creates remarkable features under a wide variety of conditions, and that the processes that build mountains are not limited to the specific circumstances that exist on our home world. The mountains are a reminder that planets are diverse, each shaped by its own history and conditions. The metallic frost on these peaks is unique in the solar system. No other place has the right combination of altitude, temperature, pressure, and atmospheric composition to create this phenomenon, where heavy metals condense from the air and settle on the highest points. The frost is not dramatic. It does not fall as visible snow. It accumulates atom by atom over millions of years, creating a thin layer that alters how the surface reflects radar. The frost is a quiet process, patient and persistent, operating on timescales that dwarf human civilization. The exploration of Maxwell Montes has taken you from the summit, down the slopes, through the transition zone where the frost disappears, and into understanding of the geology, the atmosphere, the formation, and the broader context. The journey has been slow and thorough, examining the rocks, the coating, the temperature gradient, the composition of the air, and the highland region of Ishtar Terra. Each part of the journey added to the understanding, building a picture of this alien landscape through observation and explanation. The mountains will continue to exist long after this exploration ends. The summit will remain at 11 kilometers altitude. The temperature will stay around 380 degrees Celsius, and the metallic frost will continue to condense from the atmosphere at its slow, steady rate. The rocks will fracture gradually under thermal stress. The dust will settle in sheltered areas, and the landscape will change imperceptibly over millions of years. The mountains are patient. They do not need observers to exist. They simply are. The knowledge we have of Maxwell Montes comes from the effort to understand our neighboring planets. The Venera missions in the 1980s and the Magellan mission in the 1990s provided the radar data that revealed these mountains, showing their height, their structure, and the bright reflective coating at the peaks. Future missions, including Veritas and Envision, planned for the late 2020s or early 2030s, will add to that knowledge, providing higher resolution maps and more detailed measurements of surface composition. Each mission builds on the previous ones, and each new observation adds detail to the understanding. Venus is a world that could have been similar to Earth early in its history. Some scientists think Venus may have had liquid water oceans 2 or 3 billion years ago, when the sun was cooler and the planet's atmosphere was different. A runaway greenhouse effect eventually heated Venus to its current extreme temperatures, boiling away any oceans and creating the thick carbon dioxide atmosphere that exists today. Understanding what happened to Venus helps us understand the range of possible outcomes for Earth-like planets. and it provides perspective on Earth's climate and what makes our planet habitable. The metallic frost on Maxwell Montes is a small detail in the larger story of Venus, but it reveals the complexity of planetary processes. The frost shows that atmospheres can transport materials over large distances, that temperature gradients create zones where condensation occurs, and that surfaces at different altitudes can have different chemical properties. The frost is a window into atmospheric chemistry, and it provides evidence that can be used to refine models of how Venus's atmosphere behaves. Small details often reveal large principles. The stillness of the mountains is perhaps their most striking characteristic. The surface has been unchanged for hundreds of millions of years. The rocks have not moved, the landscape has not shifted, and the only changes are the slow accumulation of fractures and frost. The stillness is unlike anything on Earth, where surfaces are constantly being altered by water, ice, wind, life, and ongoing tectonic activity. The stillness of Maxwell Montes is the stillness of a world where geological processes have reached equilibrium and where change occurs only on the longest timescales. You look around the summit one last time, observing the fractured rock, the coating of metallic compounds, the orange haze that limits visibility, and the sense of being at the highest point of an entire world. The exploration has been a journey of understanding, bringing this distant place into focus through description and explanation. The journey has been slow, matching the pace of the mountains themselves, settling into the environment rather than rushing through facts. The goal was to understand deeply, to feel present in this alien place, and to appreciate what exists there. The mountains remain in the darkness of space, orbiting the Sun as Earth orbits, two planets following their paths. Venus will rise in Earth's sky, as it always has, a bright point of light in the morning or evening, depending on its position relative to the Sun. The clouds hide the surface from view, but you know now what lies beneath those clouds, at least at one location. The highest peaks are frosted with metals. The volcanic rock is fractured by centuries of thermal cycling, and the thick atmosphere presses down with crushing force. The value of exploring Maxwell Montes, even remotely, lies in what it teaches us. The mountains show that planets without plate tectonics can still create impressive topography through other mechanisms. They show that atmospheres under extreme conditions can create unique chemical phenomena like metallic frost. They show that surfaces can be preserved for geological ages when erosion is minimal. And they show that the universe creates a wide variety of environments, each governed by the same physical laws, but expressing them in different ways depending on local conditions. The journey to these peaks has been an exercise in understanding an alien environment through careful observation. You have not physically traveled to Venus, but the exploration has brought the environment to you, describing what exists there in clear, simple terms, and explaining why it is the way it is. The journey has been patient and thorough, exploring the summit, the surface, the frost, the temperature, the atmosphere, the slopes, the formation, the radar observations, the context, the stillness, and the comparison with Earth. Each part revealed another facet of Maxwell Montes. The mountains stand as they have stood for hundreds of millions of years. 11 kilometers above the plains, cooler than the lowlands by 85 degrees, coated with lead sulfide and pyrite that condenses from the air. The rocks are volcanic, the fractures are thermal, and the atmosphere is thick and hot and still. The mountains are a feature of the solar system, a landmark on Venus, and a subject of scientific study. They exist independently of human observation, but knowing about them enriches our understanding of planets and the processes that shape them. The exploration is complete. The journey from summit to understanding is finished. Maxwell Montes exists right now, turning slowly in space beneath the clouds, the metallic frost accumulating grain by grain, the surface unchanging except on geological timescales. The mountains will be there tomorrow and the day after, and for millions of years to come, patient and still. The knowledge of them is a gift, a window into a world we cannot visit but can understand, a distant place made familiar through radar and science and patient exploration. The journey ends here, quietly. The mountains endure in their stillness, the frost condenses in its slow, patient way, and Venus continues its orbit around the sun. The exploration has shown you a place where it rains heavy metal, where the peaks are frosted with compounds that exist nowhere else, where the surface is ancient and preserved. The mountains are remarkable, and the fact that they exist, distant and hostile and real, is a reminder that the universe is full of places worth understanding. The silence returns now, the journey complete, the mountains waiting beneath the clouds.